Hey guys, welcome back. Today we're going to be covering circular motion. So far we've been covering the motion of objects largely as they go through space in a straight line, right? This will be the first time I think that we're going to get into detail about things that are spinning around and they have really cool physical characteristics. So let's just jump right on in. So circular motion is when an object turns about on an internal axis. So for example, here are these gears that are spinning around. The internal axis is the central hub, and you can see that there's an axis going in. It's all mounted on these axes right here. Here's another axis right here on this Ferris wheel, okay? It is undergoing circular motion or rotation. So here we see it rotating. Hopefully you can kind of imagine these things are going to be rotating around this central axis. This circular motion is characterized by two kinds of speeds. There's tangential, which is linear speed, and there's rotational or circular speed. And as we go through here, you'll find that there's a different speed for going in this direction versus what would happen if you let go and you kept going off in a straight line. What would happen there? And they're different speeds. And that's what makes circular motion sometimes not so intuitive. But we're going to work through it. Okay, so let's jump right in and talk about circular motion with respect to tangential speed. So the distance traveled by a point on the rotating object divided by the time taken to travel that distance is called the tangential speed. Points closer to the circumference have a higher tangential speed than points closer to the center. And we can see this actually exhibited on a record player, or you could even imagine a merry-go-round. We've all sat at different positions, and we notice that when this thing is spinning around on, say, a merry-go-round, things that are closer tend to not move very fast, but things that are out on the edge have quite a bit more velocity to them. Again, here we can see an object halfway across the record, so this is a bug. It's halfway across. It's going pretty fast, but if it's all the way out here on the edge at twice the radius out, it's going twice as fast. Okay, so that's tangential speed. So circular motion and rotational speed. So rotational speed is the number of rotations or revolutions per unit of time. So here we can actually see a rotation occurring, I don't know, every second or something like this. Maybe 2 seconds. Okay. So the rotational speed is the number of revolutions per unit of time. So rotations per second or RPM if you were dealing with engines, right? So all parts of a rigid merry-go-round or turntable turn about the axis of rotation in the same amount of time, right? So this whole thing takes the same amount of time no matter where you are at on this object to go all the way around the circle or all the way around the axis, okay? But the speed at different positions on this drawing are different depending on how far away from the center of that axis you are. So it turns out there's a relationship that allows us to measure that speed as a function of the radius, okay? So all parts have the same rotational speed. So tangential speed is really just the velocity. Remember, it's a vector. So this would be a tangential velocity is going to equal r. R is the radius, right? Radius r, it's the distance from the axis out to where you are rotating around. And this new letter, omega, right? And omega is this angular speed, which is the number of RPMs or the revolutions per minute or the revolutions per second, right? Actually, usually we put it in revolutions per second. And it's omega, which looks like a W. It looks like a kind of a wide W. So velocity is radius times omega. So in linear systems, we've already talked about how inertia plays an important role. Well, it's also present in rotational systems. So there's rotational inertia as well. So an object rotating about an axis tends to remain rotating about the same axis at the same rotational speed unless interfered with by some external influence. Now, it sounds a lot like Newton's first law. It also sounds like something that Galileo was saying about his rolling balls, right? Coming down the ramps. The property of an object to resist changes in its rotational state of motion is called rotational inertia. We give it the symbol I, capital letter I. And it's a scalar quantity. It's not a vector. And so this is a person, a tightrope walker, coming across the big top. And notice that he's got this huge pole. And what he's taking advantage of is the fact that he's holding it steady, which means that it has very, very low rotational inertia, if any at all. And it's going to take force coming in to make it balance off one way or the other. But because he's got it, it tends to not want to move. It wants to continue right in the same plane, and he's taking advantage of this rotational inertia to keep him from falling off of the line. So there's some properties of rotational inertia that we should keep in mind. That it's dependent upon the mass of the object, and that it's also dependent upon the distribution of mass around the axis of rotation. So in this case, we have a dumbbell, right? So we got a dumbbell, the weights are in close, and if he wants to rotate it, I'm assuming it's a he, wants to rotate it up, down this way or up, down this way, it's actually fairly easy to rotate compared to if the weights were way out on the end. It's the same amount of mass both times, but the fact that it's distributed further away from his hand makes it a lot harder to rotate. Why? Because mass further away has greater inertia than if it's really close. The distribution of mass is important. So the greater the distance between an object's mass concentration and the axis, the greater the rotational inertia. Anybody that ever does a workout knows that if they're doing a bench press, it's much easier to kind of push it straight up into the air than just taking, say, a small dumbbell, because the dumbbell can rotate very easily, whereas the big bench press weights have a large distribution of them. So they don't tend to rotate, and they're a little easier to actually manage. Another way that you can think of rotational inertia is to look at the different axes of a pen. So here I have a pen. It's actually a stylus for writing on computer screens. But anyway, you get the point. So here we have three ways that we can look at, say, a pen or a pencil. So hopefully you have a pen or a pencil in hand and you can experience this. So if you take your pen or your pencil and you rotate it like so, as we see up here in position number 1, right up here, it's actually pretty easy to spin. All right? And that's because the axis is going straight through the pen. All right? Now, the next stage harder would be to simply take the axis and put it right here in the middle. And when you do that, you're basically rotating it like this. And so when you start to rotate it through the middle, you'll realize pretty rapidly that's a lot harder to rotate it this way than it is to simply spin it in your hand like this. Very easy to do this, harder to do this. And of course, hardest yet would be to do the third scenario, which is to grab the end right here and to rotate the entire thing around, right? So if you're doing this, it almost wants to flip out of my hand, but I can't even do it very fast. So this would be the hardest to rotate it around the vertical axis passing through the end. So the distribution, right? So the mass is the same in all these situations, but the distribution of that mass and how I'm swinging it around has a tremendous effect on its rotational inertia. All right, so that means that all objects have different formulas that describe their rotational inertia, and not only just the object itself having its own formula, but the way it's spinning in that object produces its own formula. Now, many of these are derived using calculus and so a little advanced trigonometry. We're not going to worry about it at this point. We're just going to have some equations here, and you may or may not find them useful when you're going through the homework. Okay? So rotational inertia depends upon the shape of the object and its rotational axis. So in a simple pendulum, it's inertia equals mass times the radius squared. But if you have a hoop, about a normal axis, so the axis goes right through the middle of the hoop, right? It doesn't actually touch the metal, it goes right through the middle. And you spin it around in a circle like a hula hoop. This would be the inertia. But if you spin it the opposite way, right, you put the axis right through the edge of the hoop and you spin it around this direction, then all of a sudden you get a very different equation, right? The inertia is half mr squared. So it's going to be half of what the inertia is here. So the orientation of that rotation is important as well. Just as we were talking about, right? We have a pen, it's got different inertias depending on which way we spin it. If we do it like this, or if we do it, spin it right around the axis or whatever. Okay, so you get the idea. These are here also for reference. Spheres and cylinders and sticks, things like this. So you can kind of surmise from our experience from Newton's first law that if you're going to have inertia, there's going to be a force involved. And in rotational dynamics, we don't actually have force in the way that we typically think of it. Instead, we use something called torque. Okay, so torque is the tendency of a force to cause rotation. All right, so torque depends upon three factors: the magnitude of the force, the direction in which it acts, and the point at which it is applied on the object. So imagine you have a ball that's rolling down a slope or something like that. Whenever you reach down and you put force on it and you spin that ball even faster, maybe you're pushing it down the thing, you're actually applying a torque as you rotate it, as opposed to just pushing it with the palm of your hand down. I'm saying get down and actually put a tangential force down on the ball to make it spin faster. That's torque. And so here we actually see a real nice demonstration of what torque is and how it works. First off, let's go over this equation just to make it clear that torque is basically T, or tau is actually how it's usually represented in the literature. So tau, which is the Greek letter T, it looks almost exactly the same, is equal to F, and for all intents and purposes, this is actually a cross product, F cross R, but it's the same thing as F times R. We're not going to use any trigonometry in here, so this is going to make it nice and easy for us. So in this case, R is the radius, or the lever arm length. And it obeys something called the right-hand rule in physics. Let's describe this here in a moment. But here we see an image of a weight that is being swung around almost like a pendulum. It's being the force is being applied. There's this purplish blue color. So there's the force coming and bringing it in this direction. Now the force reverses and comes the opposite direction. Okay, and the R is consistent here. R is this red thing here. So if we want to measure the torque is R times that blue force. That's going to give us the torque. Now the torque direction, you'll notice, goes up as it comes, so it's up, and when it goes the opposite direction, it goes down. And that's a consequence of the right-hand rule in physics. Right-hand rule is something that you will find in physics over and over and over again. So as the ball moves into the screen, as it is doing right now, and then now it's coming back, you'll notice it's rotating in different directions. So as I hold up my hand, hopefully you'll be able to see this in the picture. But at this point, the ball is now moving into the screen, and notice that I'm putting my fingers into the direction that the ball is going, but my thumb is sticking up. So that's the right-hand rule. My fingers are going in the direction of the force, but my thumb is showing the direction of the torque. All right? So you'll notice, look at this image, it's coming back the other way, it's reversed, right? The force is coming back towards me, so my thumb is upside down, now it's going the other way, reverses, comes back this way, and you notice the torque is constantly changing orientation from up to down in response to where that ball is in that image. Okay. The second one down here is a momentum. We're going to come to angular momentum a little later on in this talk. So back to torque. So how do we get torque? Well, first off, think of torque as kind of the rotational form of force. Think of it that way, right? And it's based upon the radius of the object. So we have three pictures here. This is a gentleman using a wrench. He's got different angles on it. So when he pulls on it, this is at a 90-degree angle here, but it's not at 90 degrees to the wrench. Something like 45 degrees or whatever it is what he's actually pulling. It means he's not getting a direct pull on it. So he's not getting good torque on it. So in the first picture, the lever arm is less than the length of the handle because of the direction of force, right? So he's not actually pulling straight up and getting the maximum torque. So it's the same thing as not pulling it all the way at the end. Whereas in the middle picture, look, he's at a nice 90-degree angle. This force is straight up, right-hand rule, right, playing out. And what is the consequence of this? Actually, I should go like this with your right hand. As the force goes to the top of the screen here, he's going to get really good torque of the lever arms times the force, so lever arm is equal to the length of the handle. So this is the second best torque example. Now, if I want to really crank down on this bolt, I need to actually get a longer lever arm, right? Because it's force times radius. So in this case, lever arm is longer than the length of the handle because we put a lever arm extender on here, and we have a longer arm. The force is still the same, but we're able to extend much greater torque on here, which is the reason why we can spin that bolt even easier with a longer lever arm. Okay, so I've kind of been implying it, especially when I was going over the images a little earlier of the hoops where the center or where the axis of rotation goes through the middle of the hoop. Let's go back to that really quick, right here. So, but notice there's no material here. That is an interesting thing, that the physics actually goes right through. There's actually an axis that goes right through it and that controls this hoop, but there's actually no physical existence for it here. All right, so that brings us into this concept called center of mass. Let's come back to this. So the center of mass is the average position of all the mass that makes up the object. Okay, so on that hoop, even though it's a nice circular hoop like so, it behaves as though it's a point mass right at the middle. Right, for all intents and purposes, it can behave that way. The center of gravity is the average position of weight distribution. Now, remember that weight and mass are proportional through g, and center of gravity and mass usually refer to the same point of an object as a consequence, right? If you know that they're proportional, they make them interchangeable terms. So center of mass and the center of gravity, same thing. All right, so we might be asking yourself, what is this bizarre image of a human skeleton? This is a computer-generated image. This little blue spot right here is the center of mass of a gymnast doing a tumble. So it turns out that this is, in fact, the center of mass. If you put your arms down, you put your legs down, this person is actually spinning around something that's actually outside of their body. So that's pretty cool, actually, and that's used by pole vaulters to get over a pole vault bar. And I probably should have put an image of that there, but you can imagine it. That you can put your center of mass below the bar and still get your body over it. And this is exactly what they take advantage of. A gymnast as well. So center of gravity can also be used to do stability studies. And the most famous example, of course, is the Leaning Tower of Pisa. This is a place I actually visited on my honeymoon. It's tipped over. There's no doubt about it. It's kind of a creepy place to stand, but it's stable. And the reason why it's stable is because of a principle that exists regarding the center of gravity, that the location of the center of gravity is important for stability. If we draw a line straight down from the center of gravity, okay, just like what we have here, here's the Leaning Tower of Pisa, center of gravity is here, and it falls inside the base of the object. So let's draw that arrow down. Yep, it stays within the base, so the base goes from here to here. It is in stable equilibrium. It will bounce. Okay, so as long as that arrow falls within here, you're okay. If it happened to fall out here, it's going to fall down. Okay, if it falls outside the base, it is unstable. Pisa would fall right over. Cool. All right, so we now have an idea of what center of mass is, what rotational inertia is, rotational velocity, angular speed, all that stuff. We have a couple more things we need to add to our growing list of vocabulary in this lesson, and that is centripetal force. Centripetal force, and there will be another force, or pseudo force actually, that we're going to talk about after this. So centripetal force is any force directed towards a fixed center of a spinning object, right? So as this man is spinning this thing above his head, okay, there's tension on this cable that prevents it from flying off. That tension is centripetal force, okay? So centripetal means center seeking or toward the center. For example, to whirl a tin can at the end of a string, you pull the string towards the center and exert a centripetal force to keep the can moving in a circle. So if he was to let go, he would lose the centripetal force and the can would go off in a different direction, according to Newton's first, second, and third laws, actually. And here we see, this is kind of a cool image of somebody else learning the hard way about centripetal force. So notice that when this experiment happens, which is not really an experiment, the guy's just showing off, obviously, that when he lets go, both the forklift that he's driving and himself stop rotating. See that again. See? He starts going faster and faster. He lets go, and both stop rotating. Okay? We'll get into why that happens here shortly. All right, so there's actual equations that dictate the centripetal force. And so it's not as simple as F equals ma. It's slightly more sophisticated in a circular system, but not that much more sophisticated. So it turns out that the centripetal force depends on the mass of the object, the tangential speed of the object, and the radius of the circle. So, like all things, if you're standing here, it's a lot different force than if you're standing out here, right? So these kids are all happy, but if you get it spinning, maybe this child over here with the blue shoes and the one with the pink shoes, all right, even all three of them would probably fly right off if you started to spin it with any type of force or with any type of velocity, because the force would be pretty great. So it's force, which of course is a vector equaling mass times the tangential velocity squared, v squared, all over r, which is the radius. And that will give you the centripetal force at any given point on a spinning object, a spinning disk, actually. All right, so let's give some examples. When a car rounds a curve, so here we see a car making a curve, right? The centripetal force prevents it from skidding off the road. So here's the center of curvature, all right? And this arrow is going to be pointed right at the center of curvature, and this is the centripetal force. And as a matter of fact, the centripetal force is being exerted in the form of friction. It's a frictional force in terms of a car making this turn. If the road is wet, which reduces friction, or if the car is going too fast, which can also reduce friction or make it difficult for friction to take effect, the centripetal force is insufficient to prevent skidding off the road. So here we can see the force is not sufficient. It's a small arrow, whereas up here it's a big arrow. Remember, they're vectors. The center of curvature is still in place, but if the tendency to go in a straight line is greater than this arrow here, you're going to go off the road. So that gives rise to another force that is frequently confused with centripetal force, and that's centrifugal force, or centripetal force, as some people say it. They almost kind of run the two words together. But centrifugal force is very different. And so although centripetal force is center directed, in other words, it points towards the middle, just as we see here, right? There's an arrow. An occupant inside a rotating system seems to experience an outward force. So if this is you spinning around, you feel like you want to go out this direction, okay? This apparent outward force is called centrifugal force. However, it is a fictional force. It does not obey any of Newtonian physics because it's an effect more than it is a real force. It's an effect as a response to what is in fact Newtonian physics. We'll get to what that effect is versus what the physics are in the next slide or so. So anyways, so centrifugal force, which goes away, means a center fleeing or away from the center, whereas centripetal, of course, always is directed towards the center of curvature, which in the sense of a circle is right at the middle. All right, so a common misconception about centrifugal force is it is a common misconception that a centrifugal force pulls outward on an object, right? That it pulls it out, wants to spread it out. For example, in this image, we see that this mass, whatever it is spinning around, and at one point the string breaks on it, okay? If the string breaks, the object doesn't move radially outward. In other words, if it breaks, it doesn't suddenly shoot out in this direction. A lot of people think that it does, but it doesn't. In fact, what it does is it continues along its tangent straight line path. So tangent means a straight line that touches the circle as though it's hitting it flat right at that spot. Okay, so it will actually continue in this path to the top of the screen because no force acts on it. That's Newton's first law, right? So at this point, it's rotating. It's being pulled in by centripetal force. Centripetal force, centripetal force. Suddenly there's a break, no centripetal force to continue pulling it in, and as a consequence, it goes straight, according to Newton's first law. Object in motion tends to stay in motion. All right. So another thing we need to keep in mind are what we call reference frames. So you're going to hear, and I think we've already brought it up several times before, about how everything is relative, right? The experience that we go through is relative to what happens in the reference frame you're in. That'll become a big deal towards the end of the class, but I just kind of want to drop that little nugget in your head to kind of play with and see what you can pull out of it for now. So anyways, centrifugal force is in a rotating reference frame. In other words, if you're this bug that's in a can, and the can is being spun around, you're going to feel a force that's pulling you down. It's going to feel like gravity, right? So if you're in that rotating reference frame, this is your world. You live here. That rotating reference frame is a force in its own right, as real as any other force, ergo gravity. So this feels like gravity. And if you were living in the can, you wouldn't know the difference between Earth's gravity and this gravity here. So for example, the bug at the bottom of the can experiences a pull toward the bottom of the can. Makes sense. But it's really just a simulation, right? It's not a replacement of gravity. I've already told you that centrifugal force is a pseudo-force. It's an effect due to the rotation. It's not a force in and of itself. The only real force is centripetal force. All right, so centrifugal force can be used to simulate gravity in space stations of the future. So here we have this bug again hanging out the bottom of the can. But how's that different than taking a circular space station and just spinning it, right? So by spinning the space station, occupants would experience a centrifugal force simulated gravity similar to the bug in the can. In fact, to get Earth-type conditions, all you need to do is accelerate or to simulate an acceleration due to gravity, which is g, which is 10 meters per second squared. The space station must have a radius of about 1 kilometer. That's pretty big, right? Just say a diameter of about 2 kilometers. That's 1.2 miles across. So this would be 1.2 miles across. And then rotate at a speed of about 1 revolution per minute. So this point here would have to revolve every 60 seconds. And the feeling of living in this situation, at least here at this edge, would be like the bug right here. It'd feel like you're on Earth. Okay? And so this is what this person would feel. They would just feel like they were walking around in a normal gravity environment. All right, so just like linear objects or linear motion, there's also angular momentum. So basically, the inertia of rotation of rotating objects is called angular momentum. So, and this turns out to be analogous to the inertia of motion, which was momentum. So angular momentum is just this letter L, for reasons we're not going to even begin to go into. But this is angular momentum, L, and it equals inertia times omega. Remember what omega is? If not, go back to the beginning of the lecture and look it up. It gives you a reason to review this video, so I'm not going to give it to you. Go back there and pull it out. Where L is angular momentum. For an object that is small compared with the radial distance to its axis, magnitude of L equals mvr. So m being mass, v is velocity, r is the radius. Let's say the tangential velocity, right? This is the tangential velocity times the radius. So cool stuff, mvr. So just like we were talking about forces requiring an outside force to change at least the direction of the momentum, there's also a conservation of angular momentum. So it can be changed or moved or whatever, and you need an external net torque to make that happen. So it's basically a rotational version of Newton's first law, which is to say an object or system of objects will maintain its angular momentum unless acted upon by an external net torque, right? Torque, remember, is force times radius. So the law of conservation of angular momentum states, if no external net torque acts on a rotating system, the angular momentum of that system remains constant. Right? So angular momentum is constant. It's conserved. It doesn't matter if the object is spinning or if it's going in a linear direction. It's always conserved. Okay, and that's actually kind of demonstrated right here. So here we see a man sitting on a kind of a turntable, and he's got the weights way out on the outside, and he pulls them in. So I is the inertia, and then of course omega is the, hopefully you figured that out. Yeah, that's the angular velocity, right? And then so in this case, if he pulls it in, it reduces his inertia, but it increases his angular velocity. Here's a skater demonstrating this quite well, actually. So here she's going to pull in and she speeds right up. She increases her omega value. One more time. Neat. All right, so let's do some practice problems because this is fun stuff. So how much tension is on a horizontal cable that whirls a 10-kilogram block through the air at 6 meters per second? So whirling means spin, like it's spinning around. Ignore the mass of the cable. The length of the cable is 2 meters. All right, so it's basically, it's asking the tension. Remember, tension is just another way of saying force. Okay, so let's open up our handy-dandy program and do that. Okay, so we're told a couple of things here. First off, we're told that there's an object. It's attached to a cable. This will be the center of the arc, and it's spinning through a circle like this. And we know that there's centripetal force, and the centripetal force is manifested as tension. Tension, of course, is also, it's a force, right? So F, this is just our rotational force, our centripetal force equation, which is equal to tension, equals mass velocity squared over R. So now it's just a plug and chug, right? What was the mass? Well, remember that the mass of the object, we'll just go ahead and draw the object here, is equal to 10 kilograms. So it's 10. The velocity is 6 meters per second squared, all over an R of 2 meters, right? So R equaled 2 meters, and we got that straight out of the problem. So what does that equal to? Well, what's 6 squared? That's 36 times 10, 360 meters squared, seconds squared, all over 2 meters. Oh, and I forgot kilograms. I gotta put in my kilograms here. So I'll just say times kilograms, just to keep it honest. I should have put it right here, but I didn't. I forgot. But if my units don't work out, then I've got a problem, right? So I got to keep them all there. All right, so 360 divided by 2 is going to be, that's right, 180. This cancels with that. Kilogram meters per second squared. Hey, that's the same thing as a Newton. Cool. So the tension is 180 newtons. Neat. All right, what's the next part of that question? Okay, so the next part of the question is, what is the angular momentum? Oh, this is kind of a fun one. Of that whirling block in the previous question. So we ignore the mass of the cable, right? Because we've got to use the mass of the cable. This calculation a little dirtier, so we ignore it. All right, so this is actually pretty straightforward. We just use our equation for momentum. Plug it right in. Okay, so we just remember our equation for momentum, angular momentum, equals mvr. Okay. Do we remember the mass? Yeah, it was 10 kilograms. Do we know the velocity? Yeah, it was 6 meters per second. Do we know the radius? Yeah, we knew the radius too, right? That was 2 meters. All right, so L equals, what's 10 times 6? 60 times 2, 120 kilogram meters squared per second. All right, so you might be a little perplexed here, right? Kilogram meters squared per second. It's an unusual set of units to have, and it didn't match what we had for linear momentum. Well, but it does turn out that this is in fact the right units for angular momentum. Kilogram meters per second. Sometimes you will see it written in the literature, slightly different, as something called the Newton meter second. But to get that derivation takes a few steps, and we're not going to worry about it. You just take my word for it. If you have any questions about it, you can email me, and I will go through that explanation. But you can also find the explanation online as well. So anyways, we got one more part of this problem that we want to solve, and let's have a look at that one. Okay, so the last part of this problem says if the cable were shortened to 1 meter while spinning, right? So it's spinning up here 2 meters per second. It's got a cable, it's 2 meters long. We're shortening it down to 1 meter. What would be the new tangential velocity of the box? Do we have the keys to be able to answer this? Of course we do. The best way probably would be to use our solution from the previous question, which was angular momentum, where we got that really interesting result of 120 Newton meter second. So probably the best way to go about answering that problem is to remember what we got in the previous problem, which was that we had a rotational or angular momentum of 120 Newton meter seconds, I should say, or 120 kilogram meters squared seconds per second, I should say. All right, so let's go ahead and use this problem right here to solve this. So we know that the angular momentum is conserved, right? That L initial is going to equal L final. So we know that the initial angular momentum is going to be 120 kilogram meters squared per second. And we know that the angular momentum final is going to be equal to mv r. The only thing that has changed here is the r value, right? So we're going to go ahead and plug all that in. And it's going to be 1 meter. Velocity is what we don't know. We'll put parentheses around this. And then the r has, or I'm sorry, I've switched these around. So this is actually the value for r here. And m I'm going to put in right over here. That's going to be 10 kilograms here. All right. So it's kind of cool. Kilograms, meters squared, seconds squared. Or, didn't need to write that right there. All right. It's going to equal 10 kilogram meters and some velocity, v. All right, so we can go ahead and cross out these zeros. Kilograms cross out because they divide across from one another. Meters is going to cross with that one. And so we actually get the answer right away. That v is going to equal 12 meters per second. So basically by cutting the radius in half, we've doubled the velocity. That is exactly what we saw in our very first image of the record player spinning around, right? So we had a record player that was spinning around. We said half of the radius out, it's going some velocity, but all the way up the edge, it's going some double the speed of what it's doing in the middle. So this is demonstrating the same thing, right? So the original velocity was 6 meters, now it's up to 12. And that gives us some useful equations that we could use in our homework sets, because the homework sets are all dependent upon these concepts. That tangential speed is equal to the radius times the angular speed, and that torque is equal to force times the radius, where radius is the length of the arm of the lever, or the radius of the spinning object. The centripetal force is just force equals mass times the velocity squared over r. And of course, angular momentum is I, which is inertia, times omega. And then another way of saying angular momentum, probably even better and more useful, is this nice equation up here, where angular momentum equals mass times velocity times the radius. So if you have any questions, feel free to give me a quick email or meet me in the discussion boards. And until next time, have a good one.